I'm Dr. Roger, and today we're looking at differential equations. In particular, we're starting our look at systems of differential equations, and we start with the definitions of eigenvalues and eigenvectors. If you have matrix A times vector x equals some constant, which I'll call lambda, times the same vector, lambda is an eigenvalue of matrix A, and x is an eigenvector of matrix A and associated with the eigenvalue lambda. We're interested, for reasons we'll discuss later, in the eigenvalues lambda for which there is some vector x that is an eigenvector, and then we're also interested in those eigenvectors. Solving this, and there's a little bit of linear algebra thrown in, I would like to move lambda x to the left, so I will. Ax minus lambda x equals 0, and this is the 0 vector. I'm going to put a symbol over that for a vector. And I'd like to factor out the common factor of x, so a minus lambda x equals the 0 vector, but that's not allowed. A is a matrix, lambda is a constant, so this doesn't make sense. But I can do this. Ax minus lambda times the identity times x equals the 0 vector. The identity matrix times vector x is still vector x, assuming identity is the same dimension as x, just the square version. And that's the same as ax minus lambda I times x equals the 0 vector. You're allowed to do that because matrix multiplication is associative. You can move your parentheses. And now lambda I is a square matrix, same dimension as matrix A. So I have a minus lambda times the identity matrix times vector x equals the 0 vector. And we learn in linear algebra that if this has a solution for non-zero x, then determinant of a minus lambda I has to be 0. So for a matrix to have a non-zero eigenvector, and we generally define eigenvectors to be non-zero, the determinant of a minus lambda I has to be 0, and that allows us to find eigenvalues. So in this example, if I'm looking for eigenvalues of matrix A, I write the determinant of A minus lambda times the identity. And I'm going to set that equal to 0. Erasing my previous work. So that's the determinant of -2, -3, 6, 7 minus lambda 0, 0, lambda equals 0. And it can be written much more concisely as -2 minus lambda, -3, 6, 7 minus lambda equals 0. And typically, I'll jump from A to a minus lambda I determinant in one step rather than showing those intervening steps. It's important to know where they came from, and they came from, we need a minus lambda I to have determinant 0 for there to exist a non-zero eigenvector associated with that eigenvalue lambda. This gives me a characteristic polynomial. The determinant of a 2 by 2 is -2 minus lambda, 7 minus lambda, minus negative is plus, -3 times 6 is 18, equals 0, so that's lambda squared, minus 7 lambda plus 2 lambda is minus 5 lambda, and then minus 14 plus 18 is plus 4 equals 0. That factors nicely. They're both minus, and there are 1 and a 4. Since this product equals 0, either the first factor is 0, so lambda equals 4, or the second factor is 0. I swapped the order. So lambda equals 1. Now that I have my eigenvalues, I can find the corresponding eigenvector. And if you recall, I was saying that A minus lambda times the identity times vector x equals the 0 vector. So going to A minus lambda times the identity times vector x, that would be -2 minus 4 is -6, -3, 6, 7 minus 4 is +3, times vector x equals the 0 vector. And we notice that this gives us a system of two equations, -6x1 minus 3x2 equals 0, and 6x1 plus 3x2 equals 0. And that system is dependent. The second equation is -1 times the first equation, so I cannot solve for a unique solution of x1, x2. But what I can do is I can choose a value, and I'm going to choose x1 equal 1 because that makes the arithmetic easy, and substitute that into the second equation. So 6 times 1 is 6, plus 3x2 equals 0. Subtract 6. 3x2 equals -6, divide by 3. x2 is -2. So for eigenvalue 4, my eigenvector, and I'm going to give this a subscript of 1 and give this a superscript of 1. I won't give the vector a subscript because the subscripts tend to be components. Equals the vector 1, -2. For some applications, there is a convention that your eigenvectors will always be unit magnitude. In that case, you'll find the magnitude of this vector, 1 squared plus -2 squared is 5. Square rooted is √5, the magnitude is √5, so the unit eigenvector would be 1 over √5, -2 over √5. For our purposes, I will generally not do that unless there's a specific requirement. I'll just keep this vector because it's easy to work with. For lambda 2, our second eigenvalue, again taking the matrix A minus lambda times the identity is -2 minus 1 is -3. -3. 6, 7 minus 1 is 6. Times x1, x2 equals the 0 vector. And that gives us redundant equations. I'll just write the second one. 6x1 plus 6x2 equals 0, or x1 plus x2 equals 0. There is no unique solution, but if I choose x1 equals 1, then by inspection we see x2 equals -1, and my second eigenvector, x vector superscript 2, is the vector 1, -1. And I could normalize that to unit magnitude, but that is not in most cases necessary for differential equations. So this gives us our eigenvalues and eigenvectors. That is primarily a linear algebra skill, but it's used very extensively in differential equations when we're solving systems of linear equations. So make sure you perfect your skills with eigenvalues and eigenvectors before you start on differential equations. And come back soon for my next differential equations video. With math, there's always more.